Good morning, one and all. For the next 25 minutes of the session, we'll be discussing about mixing and compaction temperature for modified binders. So the background of the organization of the presentation will be as given in the slide. We'll discuss a few details about an overview as such about the mixing and compaction temperature regime in general. We'll move on to the modified binders, the various issues and the methods which are used for determining mixing and compaction temperature for modified binders, and we'll summarize the whole analysis. So most of us are familiar with the construction of bituminous pavements. Nevertheless, I would like to walk through in step by step the whole process in the purview of mixing and compaction regime. So we have the binder, which is obtained from the refinery, pumped into the truck, and it is transported to the HMA plant, where it is mixed with the heated aggregates. So the mixing process actually occurs in the HMA plant, after which the mixture is dumped into the truck, transported to the site where the compaction process is actually occurring. So in the process of the binder being heated, obtained from the refinery until it reaches this until its complete compaction, there are various temperature regimes or the temperature profiles to which binder is subjected to, due to which the properties of the binder change. So we accept, or we say that the short term binder is subject to a short term aging. So now that we know that mixing and compaction temperature is to be understood, we have to actually find out what happens during mixing and compaction. So we essentially know that there are two constituents. One is the aggregates, or we have stones of different size, which is mixed with the binder. The mixture is obtained and which is compacted to the final pavement layer. So we understand that the properties of the constituents will obviously influence the performance of the pavement. So here we also have the aggregates, which are relatively an inert material. So the properties of the aggregates do not considerably change even though it is heated to a higher temperatures during mixing, whereas the bitumen we use is a temperature susceptible material, and the earlier slide we saw that it is subjected to various temperature profiles. So we also understand the properties of bitumen will change with the temperature. So what is that property which we have to look into, or what essentially is the function of the binder during mixing and compaction? So during mixing, we expect the binder to coat the aggregate adequately. So we have an aggregate which is heated, which has to be coated with the binder. And during compaction, the binder should facilitate the movement of aggregate particles in order to form an aggregate skeleton. So in other words, the binder during mixing should be viscous enough to adequately coat the aggregates, and during compaction, it should initiate or facilitate in the movement of aggregate particles past each other to form a proper aggregate skeleton of required target density. So in order to highlight the property that is required, or which is a key parameter or a crucial parameter, is the viscosity of binder, which we expect it to be during mixing and compaction. So to look back on the history of identifying mixing and compaction temperatures, viscosity of the binder was estimated using Sabel fuel viscometer, which is nothing but a volumetric flow rate was assessed. That is the time required for the flow using a particular measuring geometry. So they expressed it in terms of second Sabel fuel, and later from so in the first edition of Asphalt Institute manual, which specifies the various mixing and compaction regime or the mixed design concepts, did not have any mention about the mixing and compaction temperatures. However, in the second edition, they introduced, based on the field experience, certain values which they have to adopt as the viscosity of the binder during mixing and compaction. So you can see that 85 plus or minus 10 SSF should be the viscosity of the binder during mixing, and 140 plus or minus 15 SSF was proposed as the viscosity during compaction. With the invent of technology and changing measuring geometry, kinematic viscosity concept was introduced, which is the viscosity divided by the density of the material at that particular temperature. So again, volumetric flow rate concept is being used to estimate the viscosity at different temperatures, and we use a capillary viscometer to measure the viscosity. So we have viscosity measured at different temperatures. We prepare a viscosity temperature chart, which is log versus in log scale, and from that we read the temperature corresponding to the viscosity of 170 centistokes or 170 plus or minus 20 centistokes as that of mixing temperature, and when the viscosity is 280 plus or minus 30, we read the temperature from the chart as the compaction temperature. So when Superpave mix design manual was introduced, they used a rotational viscometer for characterizing the or determining the mixing and compaction temperature. So yet again they measured viscosity at two different temperatures, essentially 135 and 165, and they plotted this viscosity temperature charts. They found or read from the chart the temperature corresponding to a viscosity of 0.17 as mixing temperature and the viscosity of 0.28 as compaction temperature. So what is it that when it comes to the modified binders, what is it that we have to look into? Can we use these same viscosity criteria or the same method to determine mixing and compaction temperature for modified binders? What are the issues when we use it? So we'll just look into that. So as far as unmodified binders were concerned, the same target viscosity values could be adopted, was adopted, and only the units changed depending upon the measuring geometry they used. Like the values remained the same, and depending upon the measuring geometry the unit was converted accordingly. However, the basic underlying assumption when use of the basic underlying assumption when use of unmodified binders was that it exhibits a Newtonian response in the mixing and compaction regime. So when it comes to the modified binder, this unmodified binder is added with a modifier and a cross-linking agent, and hence it results in a non-Newtonian response of the binder in this particular regime. So what is this Newtonian response or non-Newtonian response? So it is a, if I have to rephrase Newton's equation of viscosity in terms of shear stress and shear rate, we can say that when shear stress is directly proportional to shear rate, the viscosity remains constant, in the sense that if the material shows shear rate independent viscosity, it is said to be exhibiting a Newtonian response. However, when it comes to non-Newtonian, it would exhibit a shear rate dependent viscosity, wherein the viscosity can increase with increasing shear rate and it can also decrease with increasing shear rate. So essentially you can see that the equation has modified it in order to introduce the shear rate dependency in the as for the viscosity term. So there is shear thinning and shear thickening. As I said, if viscosity increases with if viscosity decreases with increasing shear rate, it is known as shear thinning, and when viscosity increases with increasing shear rate, it can be attributed to the shear thickening, and modified binders exhibit shear thinning in this particular mixing and compaction regime. So what are, now that we know that the modified binders show a shear rate dependent behavior, what is the issue in use of modified binders? So can we use the equiviscous criteria which we have used for unmodified binders for modified binders? Before I go into that, what is this equiviscous criteria? Irrespective of the grade of the binder, the viscosity should be the same during mixing and compaction. If I have to take an example, we have VG10 binder and VG40 binder. The viscosity of both the binders when we use it for preparation of the mixture should be 0.17 during mixing and 0.28 during compaction. So that is what is the equiviscous concept is all about. So you can see in this particular figure, this is a result obtained from NCHRP report. They have used 40 binders in order to determine the mixing temperature corresponding to the viscosity of 170 centipoise at a shear rate of 6.81 seconds. That is, they chose one particular shear rate and they tried to find out the temperature at which the mixing viscosity, that is 170 centipoise, is obtained, and you can see that, which is indicated in blue, that it goes up to 220 degrees Celsius. So there is a the results are all over the place, and there for one different binders we have a wide range of temperatures which is obtained, and also that at such high temperatures it can also lead to the separation of the binder and modifier. So the next issue being is the shear rate dependency of the modifier in this particular regime. So this particular table shows the estimates of shear rates at various locations in lab as well as field equipments. So, you can see that it goes from 20 reciprocal seconds to way up to 1,34,000 reciprocal seconds. So, there is a wide range of shear rates variation between the lab and the field equipments, all the more, and it is quite unreasonable to choose one particular shear rate and estimate the viscosity accordingly. So, hence we have to essentially quantify the viscosity as a function of shear rate. So, the figure that you see is the rheological response of a typical binder. So, this particular response can be divided into three different regions. The first being the viscosity is almost, the rate of change of viscosity with respect to shear rate is very less, and in the second zone you can see that the viscosity considerably decreases with increasing shear rate, and in the third region you can see that again the viscosity remains almost constant. So, viscosity at the limit of very low shear rate is known as the zero shear viscosity, and at a very high shear rate or infinite shear rate is known as high shear rate viscosity or infinite shear rate viscosity. So, taking these two, zero shear viscosity and high shear viscosity, into account, four different methods were proposed, out of which we will be discussing four methods. The first method is zero shear viscosity method, second being high shear viscosity method, third is steady shear flow method, and the fourth method is phase angle method. So, the first two methods uses rotational viscometer to characterize or to determine the mixing and compaction regime. So, for which we use a quart assembly, which is essentially a binder is taken in a container and it is allowed, and the spindle is allowed to rotate in the presence. So, the viscosity is measured as a resistance in the presence of the rotating spindle. In the second case, in the second set as a steady shear flow and phase angle method, these two methods uses a dynamic shear rheometer for characterizing or carrying out the experiments, which uses a parallel plate assembly wherein the binder is sandwiched between two plates and the top plate is allowed to rotate. So, in order to discuss about the zero shear viscosity, the experiment carried out is a shear rate sweep experiment, wherein the binder is subjected to shear rate increment, constant increments of shear rate. So, the equipment used again is a rotational viscometer. The test temperature is 120, 135 and 165 degrees Celsius. So, at 120 degrees Celsius we take the binder, we subject it to shear rate increments over a period of time, and we measure the variation of viscosity with respect to the shear rate. So, the data is obtained, as I said, at three different temperatures, and it is fit using a Cross-Williamson model, and we try to estimate the viscosity corresponding to a shear rate of 0.001 reciprocal seconds. So, essentially we will have three viscosities at three zero shear viscosities, that is essentially the one which we extrapolate to a lower shear rate, and at three different temperatures. So, again we can prepare the viscosity temperature charts, and from the charts we can read the temperature corresponding to a viscosity of 3 Pascal seconds for mixing, and which corresponds to 6 Pascal seconds for compaction. In the next method, which is the high shear viscosity, the shear rate sweep is carried out from 0.1 to 93 reciprocal seconds. So, this is the shear rate ramp that they have specified, and yet again the equipment uses rotational viscometer. The experiment is carried out at two different temperatures, and the results and the model used to fit the data is the inverse power law model. And here what they have suggested is to extrapolate the viscosity value or determine the viscosity value at a shear rate of 490 reciprocal seconds, and viscosity temperature charts are again prepared, and the temperature corresponding to a viscosity of 0.17 Pascal seconds is read as mixing temperature, and that which corresponds to 0.28 Pascal seconds is taken as the compaction temperature. So, when it comes to the steady shear flow method, a shear stress sweep is carried out. So, the experiment is carried out using a dynamic shear rheometer. As we saw earlier, a parallel plate assembly is used, and the test temperature is 76, 82, 88 and 94 degrees Celsius, and from this we try to find out the viscosity for a shear stress of 500 Pascal. So, there is no model which they have suggested in order to find out in order to extrapolate or something like that. So, the results which the viscosity at which the shear stress is 500 Pascal is taken at 4 different temperatures, Again we have to prepare the viscosity temperature charts, and from which the temperature corresponding to a viscosity of 0.17 is read, and that corresponding to 0.35 is read and chosen as mixing and compaction temperature respectively. The fourth method is the phase angle method, wherein a frequency sweep experiment is carried out from 0.01 to 100 radians per second and at a constant strain amplitude of 12%. The equipment uses dynamic shear rheometer, 25 mm geometry is used and 1 mm gap is specified. So, test temperature is 50, 60, 70 and 80 degree. Using time temperature superposition principle, phase angle master curve is plotted, from which the reduced frequency corresponding to a phase angle of 86 degree is read, and using these empirical relations they have found the mixing and compaction temperature. So, in our work what we did was, the binder CRMB 60, PMB 40 plastomer and PMB 40 elastomer was taken, and we tried to review the methods using the above mentioned methods. So, we see that there are wide range of temperatures which are available, like when we can take into account the zero shear viscosity method for one particular binder itself, you can see that that method does not give the same, it not only does not give a same mixing and compaction temperature range, but on the whole you can see that there is a wide range of temperatures identified as far as mixing and compaction regime is concerned using all the three methods. So, now that we understood there are a lot of limitations as far as these methods are concerned, like there is an extrapolations are required for most of the methods. Some methods give us a very low or very high mixing and compaction temperature. The rheological response of the binder during mixing and compaction temperature regime is overlooked, and in some cases the steady shear flow method could not be adopted by us because of it seemed to work with the binders which they have used as part of the NCHRP program, but it did not work with the binders which we had. So, what is the mixing and compaction temperature which actually has to be adopted? So, the methods which we discussed are detailed in this particular report which, of National Cooperative Highway Research Program. So, however, these methods are not standardized, and they also specify that a note which they have taken from AASHTO T312 saying that modified, I'll just read it out. Modified asphalts may not adhere to the equiviscosity requirement notes, and the manufacturer's recommendations should be used to determine mixing and compaction temperatures. So, what we did was we adopted the mixing and compaction temperatures as per the manufacturer recommendation for our work, and which is essentially 20 degrees Celsius more than the handling temperatures used for the unmodified binder. So, we took this VG30 binder and we determined the mixing temperature and the compaction temperature using the equiviscous concept we discussed earlier by preparing the viscosity temperature charts and reading the mixing and compaction temperature corresponding to the viscosity of 0.17 and 0.28 Pascal seconds. The aggregate temperature was however kept constant. AASHTO R30 specifies short-term aging for mixtures, which is essentially keeping the mixture after mixing in an oven at 135 degrees Celsius for 3.5 hours, after which it was raised to the compaction temperature which we got using the equiviscous concept. We allowed the mixture to stay at 150 degrees Celsius in an oven for half an hour. So, that is what we used for VG30. So, what we did was to take into account the manufacturer recommendations, a 20 degrees ramp was given to the temperatures of unmodified binders. So, you can see that mixing temperatures were increased by 20 degree, the aggregate temperatures were kept constant, the aging temperature was also increased by 20 degrees, and the same case with the compaction temperature, it was also increased by 170 degree. So, this is what was the temperatures which we followed for preparation of the mixtures. So, to summarize, we discussed about the mixing and compaction regime, that is what happens to the binder during mixing and compaction. So, what are the functions of the binder? It should essentially adequately coat the aggregates, and during compaction it should facilitate the movement of aggregates in order to form the compacted layer. What are the intricacies in use of modified binders, in the sense that there is a shear rate dependency which is exhibited by the binder in terms of modified binders. There is a shear rate dependency as far as modified binders are concerned. And as far as when we came into the methods, we discussed 4 methods essentially for determining the mixing and compaction temperatures. And when we reviewed it using the binders, we understood or we saw that there is no unique temperature range obtained for this, and the temperatures were all over the place. So what is that we are actually looking into, or what is the gap there? We understand that during mixing and compaction, the response of the binder changes from Newtonian to the non-Newtonian regime. So we have to also take into account the shear rate dependency of the binder. The temperature is not controlled during compaction. So essentially there is a combined effect of shear thinning and also the decreasing temperature, in the sense that during compaction, this is especially during the compaction, you can see that the binder will show a non-Newtonian response. The temperature is also not controlled. So what happens is that during shear thinning, the viscosity of the binder decreases though as the binder is subjected to shearing, and there is also, due to the decreasing temperature, the viscosity will be increasing. So there is a combined effect of shear thinning and decreasing temperature, which is an ongoing research here. So that is all. I would like to conclude by thanking DST for funding the project. Thank you for the patient hearing.